Hello everyone, welcome back to Maths by Harshit. I hope you are doing well. So now let's continue our question series. In this video I will discuss question number 1, second part, third part and fourth part of exercise 1.1. So I'll start the question. Let here relation R in the set A. Set A is a natural number, it is given here. Define R equals to so and so. Ordered pair x comma y such that which satisfy this property. It means R is the collection of all those ordered pair x comma y which satisfy this property. Property is y value will be equal to x plus 5 and x has to be less than 4. Okay, as R is a relation on A, so it has to be a subset of A cross A. That is the first thing. Now first of all find R explicitly or find R completely. So here A is set of natural number, that is 1 2 3 up to so on, all will come. This is set of natural number. Okay, now so the value, as they said, x value has to be less than 4, so the value of x will be 1 2 3 because x belongs to A. X belongs to A and the value of x less than 4, only 3 possibilities are we have. So if x is less than 1, if x equal to 1, sorry, if x equal to 1, then the value of y will be 6. If x value 2, then y is 7. If x value 3, y value 8. So what order pair we get? At 1 we got 6, at 2 we got 7, at 3 we got 8. So the relation R will be 1 comma 6, 2 comma 7 and 3 comma 8. Now so to check this relation R on A is reflexive, symmetric or transitive or not. For reflexive, we have what we need to check is every element of A related to itself or not under R. Here you observe none of the element of A related to itself because 1 comma 1 is not there, 2 comma 2 is not there, 3 comma 3 is not there. So how we can write this thing? As 1 comma 1 does not belongs to R, it's your choice. You can write 2 comma 2, 3 comma 3, 4 comma 4, because for reflexive at least one element of A if not related to itself, then we can imply R is not reflexive. Okay, so 1 comma 1 does not belong to R implies R is not reflexive. Moreover, you can write here also, moreover none of the element of A related to itself, okay. That's why it is not reflexive. Now for symmetric, how we can do? For symmetric, what we need to check? A comma B is there. If A comma B is there, then B comma I has to be there. But we clearly observe as 1 comma 6 belongs to R, but we observe there is no element start with 6, and 6 comma 1 does not belongs to R implies R is not symmetric. R is not symmetric. Here R is not reflexive. Here R is not symmetric. It's your choice. You can take 2 comma 7 also or 3 comma 8. Okay. Now for transitivity, for transitive. Two things are there. I will recall it again. Okay, I gave the definition of the transitive in the previous video, so you can check there also, and I will explain here also one more time. If a comma b belongs to R and b comma c belongs to relation R, then we need to check is a comma c belongs to R or not. Okay, if this is true for each ordered pair of ordered pair, then we can say, okay, that is the one thing. If this is true for each pair for each pair of ordered pair. And another definition is void situation, that is void situation. In void situation, I told that at the time, if a comma b belongs to R and there is no other element in R which start with B, okay, which start with B and end with some other element, okay, then we say that relation R is transitive. Here you can observe that this thing. Here 1 comma 6 is there. Is there any element 6 start with 6? No other element start with 6. So for 1 comma 6, as there is no element start with 6, here this ordered pair end with 6. And for transitivity, for the failure of transitivity, if we have some other element start with 6 and end with another element, then we need to check. Suppose 6 comma c is there, then we need to check 1 comma c is there or not. Then question will come that 1 comma c is there or not. But here 6 comma c is not there. 6 comma c is not there. That's why we no need to check. Okay, and hence we say that 1 comma 6 satisfy itself transitive property. Hence same for 2 comma 7, as 2 comma 7 belongs to R, but there is no element start with 7 and end with another different element. Okay, so we can say, yeah, this element is also satisfy the transitive property, and this element also satisfy transitive property. Hence, under the void situation, under the void situation, R is transitive. R is transitive because for each element of R, we do not have another element to check the transitivity. So this case is under the void situation. Under void situation, this case will come. Under void situation, R is transitive. So this implies R is transitive. R is transitive on A. I hope you understand this question. Okay. Void situation you understand or not? Because void situation is very important. How? I will explain it again. See here, 1 comma 6 is there, as there is no element start with 6. As there is no element here start with 6 and end with some other element C. Okay. So if 1 comma 6 and 6 comma c is also there, then we check 1 comma c is there or not, then question will come 1 comma c is there or not. But here as 6 comma c is not there, so inbuilt we can say that the word under word situation it is transitive. Okay, like that we will do. Now next question, the third part how it says what it says, relation R on set A 1 2 3 up to 6 and R relation defined on A, so obviously it has to be a subset of A cross A. Now they say y is divisible by x, y is divisible by x, that means second element of this ordered pair divided by the first element. So how R will come, R will be as 1 comma 1 is there or not, yeah, 2 comma 2 is there, 3 comma 3 is there, 4 comma 4 is there, 5 comma 5 is there, 6 comma 6 is there, and observe that 2 comma 4 is there, 2 comma 6 is there, and 3 comma 6 is also there. These all elements has to be in R. 1 2 3 4 5 6 7 8 9. So how many elements in R? Total 9 elements we have. Okay, now what we need to check? Reflexive. For reflexive we need to check. If we need to check reflexive, then it will be, as you can observe that how many elements in A? 6 elements are there. So reflexive means is every element of A, what we need to check here is every element of A related to itself or not under R. But you observe that 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there, 4 comma 4, 5 comma 5, 6 comma 6. It means every element of A related to itself. Okay. So what we can write here clearly? Clearly, every element of A, clearly every element of A related to itself, hence R is reflexive. R is reflexive on A. Done. Now next will be for symmetric. Now for symmetric, how we can check? For symmetric means if A comma B is there, if A comma B belongs to R, then B comma A has to be in R. That is the condition. Okay. 1 comma 1 is there, 1 comma 1 is there, 2 comma 2 is there, reverse 2 comma 2, 3 comma 3, 3 comma 3, 4 comma 4, 4 comma 4, 5 comma 5, reverse is 5 comma 5 again, 6 comma 6, reverse is 6 comma 6. Okay. For all these pair, for all these ordered pair from here to here, from here to here, all these ordered pair satisfy the symmetric property. But only because of these we can't say that it will satisfy the symmetric property. Okay, we need to check here also 2 comma 4, 2 comma 6 and 3 comma 6, for them also we need to check. But observe here 2 comma 4 is there, but 4 comma 2 is not there. For this element 2 comma 4 is there, but 4 comma 2 is not there. So it means that here we can write, change the color, as 2 comma 4 belongs to R, but 4 comma 2 does not belongs to R. This implies R is not symmetric. This thing I told you that R is not symmetric on A. So if for each pair we need to check, for each ordered pair, if A comma B belongs to R, B comma A has to be in R. For each ordered pair we need to tell. Okay, if it satisfies for some ordered pair and not satisfy for at least one pair, then we say it is not symmetric. It has to satisfy for each ordered pair which belongs to inside. Okay, now for transitivity. For transitive, here you observe that in a transitive 1 comma 1 is there. Is there any element start with 1? No. Okay. For 1 comma 1 transitive satisfy. Now I'll change the pen. 2 comma 2 is there. Okay. 2 comma 2 is there. 2 comma 2 is there. Is there any element start with 2? Yeah, it start with 2. Okay. So 2 comma 2 is there. 2 comma 4 is there. Okay. So 2 comma 4 is there. Yeah. 2 comma 4 is there. Satisfy. Any other element start with 2? Yeah, they start with 2. So for this one also make pair, for this one also make pair. 2 comma 2 start with 2, this 2 comma 2 start with 2, 2 comma 6, so we get 2 comma 6. Yeah, 2 comma 6 also there. Okay, now for 3 comma 3, 3 comma 3, is there any element start with 3? Yeah, this element start with 3. So this pair and this pair we need to make. So 3 comma 3 is there, 3 comma 3, 3 comma 6 is there. Yeah, 3 comma 6 is there. Okay, yeah. Now, is any other element start with 3? No. Complete. Now listen. 4 comma 4 is there. Is there any element start with 4? No. So it is inbuilt. It is satisfied transitive property. 5 comma 5 is there. Is there any element start with 5? No. No elements there. Okay. Satisfied. Property is already satisfied. For 6 comma 6, same thing. Now you see 2 comma 4 is there. Is there an element start with 4? Is there an element start with 4, 4, 4? Yeah, this element start with 4 and this element end with 4. So 2 comma 4, 4 comma 4, 2 comma 4. Yeah, it is there. 2 comma 4 is there. Same to same for 2 6 you can do, and for 3 6 you can do. So all the properties satisfy for the transitive. Now we can say uh, here what we are using here, we need to write that clearly. R is transitive as 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 A comma B belongs to R, B comma C belongs to R, implies A comma C belongs to R, and also some element satisfy void situation also, void situation property. So this implies R is transitive again you can write R is transitive on A. Okay, like that you can write. Because some element, why I'm writing this thing, because some element satisfy this property. Okay, some element satisfy this property and some element satisfy the board situation. Okay, that's why I'm writing both the things here. So R is reflexive on A, R is not symmetric on A, and R is transitive on A. Okay, I hope you understand this part. Now I'll start the next part. The last part is this one. See here, relation R on set of integers, it is defined, and they said x minus y is an integer. Okay, here A is infinite and there is no restriction on, because the difference of two integer, again we get integer. So we need to prove this complete relation. We need to check this complete relation in general. Okay, how we can check in general? Okay, I'll change the color. For reflexive, how you can write reflexive? Let A belongs to A equal to Z, that is set of integer, as A minus A, that is equal to 0, is an integer. Then if this property is hold, then that will belongs to in the relation. This implies A comma A belongs to R. So this implies, obviously it is true for each element. For each A belongs to A comma A belongs to R. This implies R is reflexive on A. Why so it is happening? Because every element of A, that is every integer, is related to itself under R. Okay, now for symmetric, how we can write? Let, in general we can prove A comma B belongs to Z, that is A, and what we need to assume also, A comma B belongs to R. So if A comma B belongs to R, what is the property? A minus B is an integer. If A minus B integer, minus of B minus A is an integer also. Okay, now if minus of B minus A is an integer, now tell me one thing. Here this thing written like that, B minus A, okay, and it belongs to integer. If minus 1 is integer, this has to be integer or not? So this implies B minus A is an integer. Clear? Hence, if B minus A integer, B comma A belongs to R. So this implies, as this is true for this is true for any ordered pair, any A comma B. If you take A comma B belongs to R, then B comma A has to be in R. So R is symmetric. R is symmetric on A. Done. Now for transitive. For transitive, same thing we have. Now let A comma B and C belongs to Z, with one more thing we need to know. A comma B belongs to R and B comma C belongs to R. If A comma B belongs to R, meaning is A minus B is an integer. Okay. Okay. If b minus c belongs b comma c belongs to R, then b minus c is an integer. And this thing you already know that sum of two integers is again integer. So if you can assume it is alpha, this is beta, you can write sum of two integer is again an integer. Sum of two integers is again integer. So this implies alpha plus beta, that is a minus b plus b minus c. What we get? A minus c is an integer. Now, if a minus c integer, then it means a comma c belongs to R. Okay, here you observe one thing, that a comma b belongs to R, we assume. B comma c belongs to R, we assume. And we prove a comma c belongs to R. It means whenever a comma b belongs to R and b comma c belongs to R, then a comma c has to be there. Okay, so this is R is transitive on A equal to Z. Okay, R is transitive on A. I hope you understand all these three parts. So thank you. If you have any doubt, you can do comment.